Learning maths and other subjects may feel like regurgitating things which you don't believe in. The cynicism may arise in school when a teacher labels your inherent belief as misconception, a wrong idea which must be fixed. But perhaps what you have is not a misconception, but a non-standard concept. Like many things in life, perspective matters. And so, this notion of empathy will be explored through the equation 0.9 recurring is equal to 1. The video will be narrated by me and two other characters, the teacher Carl, hello, me again, and the student Abraham.
Hello.
Now, let's start, shall we? Let's show something rather remarkable. We will show that 0.9 recurring is actually equal to 1. Well, let's say x is equal to 0.999 recurring. Then let's multiply x by 10 and do some algebra. Now, by proof by authority, we have shown that 0.9 recurring is equal to 1.
Sir, I don't agree with the conclusion nor the proof. Sir, look at this. If I just assume x is a bunch of 9s and I multiply it by 10, do some algebra, you can clearly see I get -1.
Interesting. By the same logic, you can probably show that 1 plus 2 plus 4 and so on is equal to -1. But this is probably not allowed in our number system because you are getting bigger and bigger. That being said, this can be true in other number systems.
Does that mean it can make sense to say 1 plus 2 plus 4 plus ... equals -1?
That's right. And if we have the time at the end of the class, then we can talk about it.
Cool. Anyway, I still don't believe the conclusion that 0.9 recurring equals 1. Surely 0.9 recurring is less than 1 by a really small amount. Let's call it an infinitesimal. So 1 minus 0.9999 equals 0.0001, or etc. equals 1 over 10 to the power of infinity. I guess I'm saying, like, if I take 1 from the infinite digit, I have 0.9999 recurring.
Remember that in our number system, infinity is not an actual number, so that doesn't really make much sense. Infinity is akin to potential indefiniteness, rather than an actual number. In your argument, it seems like infinity can be attained at the infinitus decimal place. Okay, it seems like you're not convinced by the previous proof, so here's another proof by authority. When you're older, you will study this thing called geometric series, which allows you to do infinite sum.
You just said infinity is not a number.
Okay, you're right. What I should have said is not infinite sum, but limiting sum, where we take the limit as n approach infinity. When we use this formula anyway, we can show that 0.9 recurring is equal to 1.
I don't get it. What do you mean by that?
Okay, fair point, given that I haven't really told you about what mathematical analysis is, which is a branch of mathematics which studies these limits and stuff carefully. Roughly speaking, we treat 0.9 recurring to be a sequence of 0.9, 0.99, and so on. And as you might imagine, the sequence is getting arbitrarily close to 1. And so we say that the limit of the sequence is equal to 1.
Sir, can you fully explain yourself?
Now here lies the contention between the teacher and the student. Are infinity and infinitesimal actual numbers or not? If it is, then we must avoid those terminology and say that the difference is arbitrarily small, rather than saying infinitely small. But if it is, then much of what the student is saying seems to make sense. There are two key ideas in order to understand the real numbers. Firstly, we would like to construct simple number systems. We will start from the integer z and then move progressively to the rationals q and then finally to the real number r. Secondly, we would like to understand various logical statements in order to articulate certain properties of number system. Let us start our discussion by talking about the integers. I'm sure you are very familiar with this object, and more so when you look at this diagram. Now, let's consider what kind of property the integers have and does not have. Let's try to show the statement that the integers are unbounded. That is to say, there are no largest element. And to do this, let's play a social game between you and I. Imagine I give you an arbitrary integer x. Then, can you find a y, which is an integer, such that x is less than y? For example, if I took x to be equal to 3, is it possible for you to find y such that y is bigger than x? And in general, can you always find a y that is bigger than my x? Have a think.
Okay, well, if you give me x equals 3, then I can just take y equals 4. So whatever x you give me, I can take y to be x plus 1.
Brilliant. What we have just showed is that the integers are unbounded. Now, mathematicians like really cool symbols and stuff, so they might represent it like this. But I didn't really understand what these symbols mean at all, and so for the purpose of this presentation, let's not bother with it. This time, let's show that infinity is not an actual number by playing a similar social game. Can you find an integer y such that whatever x I give you, y is bigger than x?
This is a little bit more complicated. Unlike the previous game, I need to specify my number y at the start. The problem is that you can always find x that is larger than my y. So no, this game is unplayable.
Excellent. To give a concrete example, if y is 10, then I can always find a bigger number than that, such as 12. What we have just showed is that infinity is not an actual number. Now, given that we understand some aspects of the integers, a natural question to ask might be, why do we go from the integers to the rationals? Well, one of the key properties which the rationals have, but the integers doesn't, is the multiplicative inverse. Again, let's play a similar game where, if I gave you an arbitrary integer x, then can you find an integer y such that the product xy is actually equal to 1? For example, if I took x to be equal to 2, can you see why there are actually no integer y such that 2 times y is equal to 1? Hence, what we have just showed is that the integers does not have multiplicative inverse. Now, let's consider the rational numbers. Here we have some list of possible rational numbers, and I would like to consider two key questions. Firstly, can the same fraction be represented differently? Or in other words, do we have some notion of equality? And secondly, are every number listed here actually valid? Have a think.
Well, I can see that 1 over 3 is equal to 2 over 6. So yes, a fraction can be represented in different ways. Now we can write any function by taking a pair of integers, but the denominator can't be 0.
Well, based on the previous observation, we can see now that the rationals are just pair of two integers, where one of them is non-zero, and applying it some notion of equality. Let's make this more clear. Let's define key operations, which includes equality, ordering, and addition and multiplication. Let's consider what equality means in the rationals. Of course, 1/3 is equal to 2/6, but one way to check this is by cross-multiplying. Hence, if we are given a over b, which is equal to c over d, we can check by cross-multiplying. We shall note the technicality that b and d, the denominator, must not be 0. We can check ordering similar to equality by cross-multiplying. We see that 1/3 is less than 2/5 because by cross-multiplying we see 5 is less than 6. To make this algebraic, we can do this. Now let's continue defining what addition and multiplication is for mild mathematical triumph. We can add two fractions by giving them the same denominator, and we can multiply two fractions by multiplying the numerator and the denominator separately. Algebraically, we can write it like this, and we should also mention that b and d must not be 0. Let's quickly convince ourselves that the rationals do have multiplicative inverse. For example, if I took x to be 2 over 3, what value of y are you going to take such that x times y is equal to 1? Have a think.
If x is equal to 2 over 3, then I can take y equals 3 over 2, which is our multiplicative inverse. In general, I can just flip whatever x you give me.
Well said. What you have just showed is that the rationals do have multiplicative inverse. Now, let's talk about the real numbers. Are you aware of the history of real numbers?
Real numbers include both the rational and irrational numbers and can be represented on a number line. I know that Pythagoras and his colleagues didn't believe in irrational numbers.
Very good point. Many Greeks thought that all numbers must be rational, and yet Hippasus, a disciple of Pythagoras, shows that square root of 2 is irrational. At that time, this number was called a logos, a number that cannot be reasoned about. When Hippasus showed them his proof, he was thrown into the sea apparently.
What a shame. He seemed like a good man. What a rotten way to die.
So, how do we define the real numbers using the rationals? Well, we can't directly define what the real numbers are using rationals because there are things like irrationals such as square root of 2. Well, in that case, why don't we think of real numbers as a journey of rationals? That is to say, a sequence of rationals that's getting closer and closer. For example, let's take square root of 2 to be a sequence that goes 1, 1.4, 1.41, 1.414, and so on, where that is getting closer and closer to the number square root of 2. One more thing, just like rational numbers can be represented in different ways, real numbers can also be represented in different ways. For example, the number 3 can be represented as a constant sequence or as a sequence that's getting closer and closer to 3. The most simplest way to define a rational number is by a constant sequence.
Why can't we write the square root of 2 equals a constant sequence of square root of 2's?
Interesting question. The reason why square root of 2 cannot be defined as a constant sequence of square root of 2 is because we are trying to construct the reals using the rational numbers. Hence, here we're using an irrational number to define an irrational number. Similar to how we define the rationals, we can define the real to be Cauchy sequence of rationals and applying it some notion of equality. Now again, we shall define key operations in order to do arithmetic, such as addition and multiplication, and most importantly, equality. So, how do we define addition and multiplication on a sequence of rationals, where each terms a1, b1, and so on are all rational? Well, given that we know how to add and multiply two rational numbers, why don't we just define it component-wise, where we add and multiply the first terms together, and so on.
Why can't we define real numbers through decimal places?
What a brilliant question. One way to think about it is to consider adding two numbers with infinite decimal places. This looks very difficult because in general there might be a carry that ripples through the number, and hence it's very difficult to find the nth position of the decimal place of the sum. Hence, in general, I think addition is very complicated. The important question to ask is, what does it mean for two sequences to be equal? And similarly, what does it mean for 0.9 recurring to be equal to 1? Well, we see that 0.9 recurring is getting arbitrarily close to 1. And so a natural definition might be that two sequences are equal if the difference between them becomes arbitrarily small after a certain point. Let's make this rigorous by using a game analogy. Now let's play the ultimate social game. Imagine if I choose an arbitrary number epsilon, then can you find a point such that the distance between the two sequences after that is always less than epsilon? Now that was a rather cumbersome definition, and symbolically we represent it like this. Even more complicated. And in fact, many mathematicians have struggled with this definition, at least initially. And so let's take it slowly and try to use this to prove 0.9 recurring is equal to 1 by definition. Firstly, let's look at the difference or the distance between these two sequences, and that is given by this. Okay, let's try to understand this by taking some examples. If I took epsilon to be equal to 1, which point would you take so that everything after that is always less than 1? Have a think.
If epsilon equals 1, then I could take the first point.
Okay, let's make the game more challenging by taking a smaller epsilon. Let's say 0.023. In that case, which point should you take?
If epsilon equals 0.023, then I could take the second point. Whatever epsilon you give me, I could always go very far into the sequence.
Exactly! I think you now understand what it means for two sequences to be equal.
Okay, I get why 0.99 recurring equals 1 according to your definitions. Does that mean the sequence 0.8, 0.98, 0.998, 0.9998, etc. would also be equal to 1 according to your definition?
That's right, because the sequence gets arbitrarily close to 1.
Here's how I would interpret this fact. Real numbers can't distinguish between an infinitesimal difference and a zero difference.
Interesting way to put it. Yes, I suppose that could be considered a limitation within the real numbers. Let's recall the definition of what it means for two real numbers to be equal to each other. I would like to highlight the importance of distance between the two sequences, which here we define it by the absolute value. And so, we can understand 0.9 recurring to be equal to 1 on the real number, which is defined to be the Cauchy sequence with some notion of equality. And that equality is in turn dependent on the type of distance we use. Now, how can we understand the equation 1 plus 2 plus 4 plus 8 and so on? Well, what we probably need is another type of number system called the p-adic numbers. Similar to how we define equality on the real numbers, we could use another sort of equality, which is in turn defined by the p-adic distance. And so, the equation 1 plus 2 plus 4 plus 8 and so on can be understood not using the real numbers, but using the p-adics, which is defined by the Cauchy sequence of the rationals with another notion of equality, which in turn is dependent on a different metric, called the p-adic distance. The student checked back on his note. In the real number system, infinity is not a number, but a limiting process. Infinitesimal difference cannot be distinguished from zero difference. He recalled back at how the teacher explained various number systems. Multiplicative inverse doesn't exist in integers, and so the rationals were created. Irrational doesn't exist in rational number, and so the real numbers were created. Now, infinity and infinitesimal doesn't exist in real number. So it was clear what his goal was now.
Sir, I'm sorry, but I still believe in infinity and in infinitesimals.
Well, there's nothing to be sorry about. Tell me what you're thinking now.
So our discussion on real numbers have inspired me to create a new number system. Let's call it hyperreal. Analogous to the construction of real numbers, hyperreals are a sequence of reals and applying it to some notion of equality. Notice we are not restricted to a Cauchy sequence now because we want to be able to represent infinity. Let's define several operations such as addition and multiplication. Most importantly, understanding equality and ordering will let me show you why 0.9 recurring is less than 1. We can add and multiply two sequences component-wise, similar to before. Now onto the important concepts. Unlike the reals, we need a stronger notion of equality. Two sequences getting arbitrarily close is not good enough. Intuitively, we say two sequences are the same if almost all terms are the same. To put it another way, finitely many terms are different. Just like how the rationals can be represented as a constant sequence in the reals, we represent the reals as a constant sequence in the hyperreals. So now, by definition, we see 0.9 recurring is not equal to 1.
Yes, I understand your point.
Ordering can be defined similarly. A sequence X is smaller than Y if finitely many terms are greater than or equal to Y. Can you see why, from the definition, 0.9 recurring is not equal to 1?
Let me have a think. Yes, you're right. So since no terms on the left-hand side are greater than or equal to the right-hand side.
Now consider the sequence H and H plus 1.
Let me guess. Those represent your infinity.
Exactly. We can see from the definitions that 3 is less than H. This is because only the first three terms on the left-hand side are greater than or equal to the terms on the right-hand side. By similar argument, we can show 100 is less than H. In fact, whatever real number x you give me, x is less than h. One more thing, we can also show that h is less than h plus 1, which reminds me of how we showed various properties of the integers. So in honor of that, I'll call h and h plus 1 and numbers like those infinite hyperintegers. An interesting question to think now is, how do we visualize the hyperintegers? Given that h is bigger than any finite real number, I think it looks like this. A hyperinteger has both finite and infinite components, and they can both go on forever in either direction. Now similarly, let's consider the number 10 to the minus h. The hyperreal number 10 to the minus h is non-zero, but is smaller than every real number. So let's call this an infinitesimal.
That's very interesting. So you have constructed your infinite and infinitesimal element.
Don't stop me yet. So far, I've tried to articulate myself clearly, but now I'm going to make a leap of faith here. I think that whatever succeeds for the finite also succeeds for the infinite. For example, we played the game that told us that the integers are unbounded. Well, we saw earlier that the hyperintegers are also unbounded. With this heuristic in mind, let's now address some of my previous concerns. Using the heuristic, we can say if finite sums work, then infinite sums should work. And I don't mean infinite sums like the limit you talked about. I genuinely mean like taking n equals h. So maybe I should call it h infinite sum. Maybe it's also possible to write a decimal expansion for hyperreals. If we have a decimal expansion with n nines, then we can also have h nines. Now I've put a semicolon between the ... to acknowledge the separation between finite and infinite hyperintegers. Anyway, we can do something very similar here as well. In the real number system, 0.99 ... converges to 1 because infinitesimals can't be distinguished from 0. But now we see that it is less than 0.99 ... which is less than 1.
Now, of course, from a technical standpoint, there were numerous gaps in the student's argument. One criticism is the validity of heuristic he proposed. There exists a statement that is true in the real but not in the hyperreal. Not every non-zero element has a multiplicative inverse, like this. However, with modern tools of mathematics, we can solve this. Another interesting point is that, as we have seen in the video, many structures in mathematics are in some way incomplete. We constructed the real numbers since there were a sequence of rationals which should potentially converge, but did not actually converge. Similarly, there are sequence of statements about the reals that are potentially satisfiable, but are not actually satisfiable. Now, enough about the mathematical technicalities. What's most important was that good learning has taken place on both sides, for the student and for the teacher. The student has fully internalized the teacher's concept of the real numbers and has in turn provided the teacher with a new perspective by articulating his non-standard concept into something genuine, non-standard analysis. For a day of schoolwork, it was a bloody good job.